Hello everybody, this is 2019 Math Prize for Girls, problem number 19, and here's a view of this problem. We are given this number n written in base 27 as such, where each of these letters represent numbers, like the letter A represents 1, B represents 2, and so on. In base 27 you have 27 different digits, and here in the English alphabet we have 26 letters, so none of these is 0 actually. So basically, if this number in base 27 is given, just convert it into base 10, right? And then lastly divide it by 100. What's the remainder? So obviously let's directly do the conversion, right? So n is just equal to, well, z is in the units position, right? So this is, and it's the 26th letter of the alphabet. So, and we are in base 27, so let me write it as 27 to the 0th power. So that's the units digit. That's the, not the tens digit, that's the 27's digits. So we have 25 times 27 over 1. Yeah, so the next one is x, which is the 24th letter of the English alphabet. So 24, times, and it appears on the 27 squares digit, and so on. If you keep going like this, we can write, for instance, B and A finally. B has a position, is 2, right? It's the second letter, times 27 raised to the power. If you observe that the coefficient and the exponent, they add up to 26 regardless, right, for each term. So therefore 2 plus, and this one would be a 24. And lastly, A has a position 1 times 27 raised to the power 25. That's it. The question basically is asking for this number modulo 100. Awesome. So how do we do it? Any ideas? Well, I guess I'm hearing you guys shout. It feels like Chinese remainder theorem, of course. The moment you use the word theorem, and I got this from Evan Chen mentions it, people are kind of worried, right? So, and then they never really try to understand it. But this is a very intuitive result that it should be in your toolbox regardless, right? So basically what this says, what Chinese remainder theorem says is, if you have a large mod like we have it here, you can split it into smaller mods. So instead of solving one congruence, you can solve a system of congruences, right? So that's the spirit of the Chinese remainder theorem. One congruence depends on how this thing is factorized, right? Turns into or equivalent to a system of congruences. That's it. And somehow it's easier to work with lower modulos. Obviously 100 is 4 times 25. 4 and 25 are relatively prime. So therefore we will do it in 2 steps. I need to calculate the value of n modulo 25, and then I need to calculate the value of n modulo 4 as well, and then boom. And then I will be able to combine them without using the formal way of the statement of the Chinese remainder theorem. So the Chinese remainder theorem as such is just a technique, right? So it's like something in your toolbox, like Euler's theorem. And the same way here. So Chinese remainder theorem, we'll just make use of it directly. It's natural. I think this one is easier, so let's start with this one. Obviously 27 is minus 1 mod 4, so as a result let's start with this one first, right? So n is congruent to, well, it is 26 times 27, we are replacing it with minus 1 raised to the 0th power, plus 25 times minus 1 raised to the 1st power, and so on. 24 times minus 1 raised to the 2nd power square, and so on. We go all the way up to 2 times minus 1 raised to the 24th power, plus 1 times minus 1 raised to the power 25. And this is just equal to, well, this is an even number, so 26. This is an odd, right? So minus 25 plus 24. Next one will be minus 23, and so on. All the way up to 2. And this one is a plus, right? Minus 1. And, oh gosh, this is a horrible one. Horrible turn of events. Horrible. Okay. Yes. So we can combine them like that, and indeed this is just congruent to 13. Everything mod 4, obviously, modulo 4, and 13 modulo 4 is just a 1 modulo 4. Yes. Okay, so what's next? Well, we are done with modulo 4. Now the second part of the question, we need to also evaluate this number n modulo 25, and then we will have our desired result, hopefully. So n is congruent to, okay, let's do a similar strategy. 26 times, replace 27. 27 modulo 25 is just a 2, so 2 to the 0 plus 25 times 2 to the 1, right? Plus 27 squared, so 2 squared, right? So 24 times 2 squared plus dot 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 plus 2 times 2 to the 24 plus 1 times 2 to the power 25. That's it. Well, the initial terms are relatively easy to calculate, but as you progress towards the end, 2 to the 25, for instance, modulo 25, what is it, right? So, or 2 to the 24. So before we look into individual things, it might be a better idea to simplify this. And indeed, you've seen this type of sums before, I guess, right? So there's this super nice, cool trick of the double summation trick, right? But for those of you who do not know how to deal with double summation signs, it's probably better to have a visual example, and here it comes. So what I will do is I will split each of these terms by their coefficients in the following way. So I'll write this as 2 to the 0 plus, we have a 2 to the 1 here, plus 2 squared plus dot 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 plus 2 to the 24 plus 2 to the 25. Well, I'm not done yet, right? I have 26 2 to the zeros here, or 26 ones. I only used one of them. Okay, so let's do it again. There's 25 to, yeah, so more dot 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 plus 2 to the, so therefore there's another 2 to the 25. Oh, we are done, right? So there's no other 2 to the 25, so that I used it. And then, well, we need to keep going. So 2 to the 0 plus 2 to the 1 plus 2 squared plus dot dot dot. So the next one will end earlier, right, at 2 to the 23. Do you guys agree? And then keep adding them, and eventually 2 to the 0 plus 2 to the 1, maybe 2 squared plus 2 to the 0 plus 2 to the 1, and lastly 2 to the 0. So in total, does everyone agree? I hope we do, right? That we have 26 2 to the 0s here, and then we have 25 2 to the 1s, and so on, right? We have this shape which is like what? It looks like a, let's use orange. This whole thing looks like a triangle. This is the spirit of this double summation that we talked about, right? Yeah, so the sum of all these terms here is the same as this one, right? So all I did was to split each term into individual units, if you will. Now we're ready to sum each row, right? So that's the whole thing. Okay, I lost my color. Okay, there you go. All right, so let's find the sum of individual rows, and then we can add them to get the column sum all together, right? So that's the spirit of a double summation. So 2 to the 0 plus 2 to the 1, 2 squared, 2 to the 24, all the way up to 2 to the 25. That's just 2 to the 26 minus 1, all divided by 2 minus 1, which is just 2 to the 26 minus 1. The next one, pretty much the same thing, 2 to the 25 minus 1. The one after that, 2 to the 24, because it ends at 23, right? Minus 1, dot, 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 a bunch of them, right? So next one, the one, so this one, 2 to the 0 plus 2 to the 1 plus 2 squared. I know it's easy to compute, but I'm not going to compute it that way. I'm just going to write this fancy. So this is just a partial geometric sum, right? And then this one is 2 squared minus 1. And then this one is just 2 minus 1. I know, silly. Why would I write 1 as 2 minus 1? But yeah, you will see. Now all we need is just to add up these numbers. And finally, so this implies n is just congruent to, well, we didn't even do any congruence yet, right? Well, actually we did. Yeah, so the 2 here, it used to be 27. Yeah. Anyhow, so we add all of them. We just realized that we have 2 plus 2 squared. I'm just adding these, the 2 to 2 squared, the 2 cubed first, right? So 2 cubed. That's a horrible 3, plus 2 to the 24, 2 to the 25, plus 2 to the 26, And then we have minus 1, blah, blah, blah. A bunch of minus 1s. How many? How many rows do we have? How many 2 to the 0s? 26 of them. So minus 26. So wait, there's another partial geometric sum. This is just 2 to the 27 minus 1 over 2 minus 1, except that it's missing a 1 in the front, so I need to further subtract the 1, and there's still a minus 26 here. But this is just 2 minus 1 is just a 1, so 2 to the 27 minus 1 minus 1 minus 2, so this is minus 28. And now I should, congruent maybe, I need to calculate this whole thing in modulo 25. Well, modulo 25, 28 is just, minus 28 is just minus 23, minus 3 I should say, or plus 22, right? But how about 2 to the 27? Again, just like Chinese remainder theorem, Euler's theorem would be super useful, so let's make a note here. Euler, so by Euler's theorem, so I'm kind of refraining to use the word theorem, so why don't we just delete those words? Chinese remainder trick, how about that? Trick. So when you say trick, people will not be as scared. And the same thing, the Euler trick. How about that? Euler trick, Euler's trick, or Euler trick. Okay, anyhow, a trick. Yeah, so 2 to the power, 2 and 25 are relatively prime. Phi, the totient function of 25, is congruent to 1 modulo 25 by Euler. So all I need is to calculate phi of 25, which is just the same thing as phi of 5 squared, which is 5 squared minus 5. Oops, that's a 20. So this implies, well, Euler's trick implies 2 to the 20 is congruent to 1 modulo 25. In our case, we have 2 to the 27, right? So that's a 7. So therefore, we can split it into 2 pieces. So therefore, n is congruent to 2 to the, well, I can write it as 2 to the 20 times 2 to the 7 minus the 28, we realize is just a minus 3 or a 22. Everything modulo 25. So 2 to the 20, we just said it. It's just a 1, so that's the whole point. And 2 to the 7 is just 128. Actually, let's just leave. Okay, so first of all, yeah, this was plus 22, but actually I want to leave it as minus 28. It's easier. 128 minus 28, that's just congruent to 100 modulo 25. Hey, 100 modulo 25 is just 0. So now back to the original formulation. So we realized that modulo 25, our number n, is congruent to 0. Okay, here. So n, let's write it with maybe black color. So n is congruent to 0 modulo 25. It is congruent to 1 modulo 4. 1 modulo 4. So as a result, what would be the smallest number, which is 1 modulo 4 and 0 modulo 25 at the same time, right? Do you guys agree? So what is the small, and the answer by Chinese remainder theorem, because we are investigating is mod 100, there exists one answer, right? So one solution. And yeah, so one way to do it is just, hey, all I do is just check the multiples of 25, whichever is the smallest multiple of 25, which satisfies also the second condition works. So the smallest multiple of 25 is 0, right? So where n is congruent to 0, right? So but 0 won't work because n is 0 mod 4 is not 1. Next one would be 25. Is 25 working? Yes. 25 gives you n congruent to 1 mod 4, and that's it. That's the answer. So this whole number, that thing, if you were to divide it by 100, would have been congruent to, so the remainder would have been 25. 25 modulo 100. So what did I like about this problem? A couple of things. The way we used different techniques. 3 techniques altogether. 1, Chinese remainder theorem. 2, that's double summation trick. And 3, Euler's trick. 3 tricks. And we're done.